Okay, today we're going to talk about a concept called free energy, and this is really confusing. I'm not trying to, get you really pumped or anything. There's another video that I found of someone who does a really good job of explaining the concept, so I'm going to go with what I have, and then I'll show you this video in class and give you the link as well. But free energy is abbreviated by this letter G, and it helps you determine the temperature dependence of spontaneity. Okay, now it doesn't necessarily have an explanation as much as just a definition. And the definition of free energy is this equation over here, where you have G, which is your free energy, you have H, which is enthalpy, you have T, which is temperature, and you have S, which is entropy, or spontaneity. Okay, so, and the video that I'm going to show you, I think, does a good job of explaining what these are and how they impact it. So I'm going to kind of jump into my math, and then we can watch that to help us back up if we need to. But you've got definition of G, and then at constant temperature, this is an equation that we need to be familiar with. The delta G is equal to the change in enthalpy, the temperature, and the entropy. So it's a way of looking at how much, I like to say available instead of free. I think it's easier to understand that way, but it's just kind of the way that things are explained. Okay, and this is just another form of the equation. And I'm just going to show you another way to kind of manipulate that equation. So if you take this equation right here, okay, you can also kind of manipulate it, start pulling into the whole delta S, the entropy of the surroundings and of the system. So for a reaction at constant temperature and pressure, you can get another variation of those equations where the delta S of the universe takes into play both the delta S of the surroundings as well as the free energy and the temperature. Okay, so more importantly, we get back to this whole sign stuff. Here's your your other manipulation of equations to figure out that, here's your delta S of the universe can be equal to this, or the one that we were using earlier to determine the signs and such. So, okay, so what sign would the delta G of a reaction have? If the delta S of the universe is positive, it's going to have to be negative. Okay, so this is important. If something is going to be spontaneous, okay, we now have a situation where the entropy, we know the entropy is going to be positive, and we know that the delta G is going to be negative. Okay, so that's going to help us drive that. Okay, why? And this is kind of shows the math a little bit later, but at constant temperature and pressure, the process is spontaneous in which the free energy decreases. Okay, so that's kind of what we're looking at here, is that the free energy, the available energy decreases because it's being used up. So you're going to have your delta G be negative. So delta G is kind of the same as delta S. If you're using up free energy, you're making things more random. So they kind of go hand in hand. I think if you can lock onto that idea, it hopefully will make things a little bit easier. Okay? All right, so for example, here's this whole, now we're going to go to water melting, going from a solid to a liquid. Okay, so delta H at standard conditions, that's just what that prime sign means, 6.03 times 10 to the third joules per moles, and your delta S at standard temperature conditions is 22.1 joules over moles times Kelvin. Since the reactions values are, okay, delta H is positive, delta S is positive, so we have increasing chaos. Since the reactions values are in opposition, the temperature determines the spontaneity, because remember, if we had positive S, that's good for spontaneous. Endothermic, not so good for spontaneous. Exothermic is what would make it automatic. If you have an exothermic reaction or in delta S, automatically going to be spontaneous. But we got to do some math first to figure out the alternative, or to figure out if it's spontaneous. So since the reaction values are in opposition, that just means that one is yes and one is no. Temperature is going to determine spontaneity. So at negative 10 degrees Celsius, is it spontaneous? Okay, so here is our delta G equation. This, remember, is my delta H minus temperature, did a bad job of not writing my equation here, or delta S. So what we're just solving for is we're solving for delta G, and we're simply looking at the sign. The reverse is spontaneous simply because it has a positive sign. That's it. Doesn't matter the magnitude. If it's negative, it's going to be spontaneous. If it's positive, it's not. It means that the reverse is spontaneous. At negative 10 degrees Celsius, which makes sense because at negative 10 degrees Celsius, that's below the freezing point of water, so it's going to freeze. It's not going to spontaneously melt when it's below the freezing point. Okay? It's just the math that proves what we know from common sense. All right, another way to check for spontaneity would be to check to see if the delta S of the universe is positive. How can we solve for delta S of the surroundings? Well, we can use the delta H prime and T. So because of that new equation that we just had, so if we have a 10 degrees Celsius is spontaneous, we've got delta S of our surroundings. It's going to be equal to our delta H over our temperature. Okay, and so that's going to be negative 22.9 joules over moles times Kelvin. So same thing, since delta S of the universe is now negative, well, it's still not spontaneous simply because you have a negative. So it just shows us that both of those support that. Okay, is it spontaneous at 0 degrees Celsius? Well, when we solve for it, guess what? We get flat out delta G. Remember, here is our delta H minus T times delta S. It's equal to 0. Well, if it's equal to 0, it's at equilibrium, no shift, which again makes sense. The 0 degrees Celsius is right at the freezing point slash melting point, so it's at spontaneous. And same number of particles you get that are freezing, there are some that are melting, and so from the outside it doesn't look like anything's changing, even though there is this dynamic situation that's going on right at the, breaking point. Well, and if you solve for it, okay, your delta S of this universe is equal to 0. So same thing, you're going to also get a situation where it mathematically proves that or supports the idea that it's at equilibrium. Okay, spontaneous at 10 degrees Celsius. Now we know the answer. Remember, what are we trying to figure out? Well, will water go from solid to liquid? Okay, that's the shift we're looking at. Well, finally we get to 10 degrees Celsius, which again we know is above the freezing point. We have a negative delta G value, so it's going to be yes, spontaneous. We have a positive delta S value, so yes, spontaneous. So big take-home message here is you do this math, and then what's most important is the signs, okay, as we've seen with thermodynamics as well. All right, so this is just another nice summary chart, table 16.4. It just shows us what we kind of had at negative 10, 0, and 10 degrees Celsius to show spontaneity, not spontaneity, different ways to study it, and some of those different equations. Here's our delta S of the surroundings equation. Here's our delta G equation as well. Okay? All right, so when H and S are in opposition, again, the spontaneity determines on the temperature, which we just saw. So if it's in opposition, which is a little bit different here because remember it's not different signs, it's different being favored differently, because remember positive delta S is good, positive delta H is bad, not bad but not spontaneous because it's endothermic, whereas negative delta H is positive because it's exothermic, and negative delta S is negative or bad because it doesn't increase the spontaneity, it goes opposite. So exothermic reaction is typically spontaneous at a low temperature, right? And this just summarizes again some possible combinations of delta H and delta S. If one, remember these are all happy, where are we, right here, because you have exothermic and high entropy. This is never going to work because you have, shouldn't say never, but, whoa, there's my mouse, there we go. These are never going to work because you have endothermic and decrease in spontaneity. And then these two are in the middle. So when you have a high randomness and endothermic, this is going to be very high temperatures, where that exothermicity, well, how's that for a word, is pretty not important. And then on the flip side, it's going to be very low temperatures. Okay, so you should be familiar with these patterns and be able to know where that comes from or why that's the case. Okay, what temperature is this reaction spontaneous at 1 atm of pressure? This is liquid bromine going to gaseous bromine. So in essence, you're trying to figure out what is the boiling point of this. Okay, your delta H for the reaction is 31.0 kilojoules per mole. Okay, that's endothermic, so that's not so great. Delta S here is positive, so that is so great. So we got to figure out, we're looking for the boiling point. We're looking for when delta G is equal to 0 here, because it's at, again, equilibrium. Okay, so we're just going to set up an equality. We want delta G to be greater than 0. So what we have here, if you think about equation-wise, again, did a bad job of not writing these out. Got delta H, T, and delta S. Okay, so again, I'm really just solving for it and then making sure it's over that temperature. Okay, so again, I do have to, because I got a negative sign, I end up switching my signs down here. So that goes back to some inequality math, but it's going to be spontaneous greater than 333 Kelvin. Okay, that's our boiling point of liquid of bromine. Okay, which again is pretty high, which is why bromine is a liquid at room temperature. So if it's greater than 333 Kelvin, it's spontaneous, it will boil. Less, the reverse is spontaneous, or the condensation. If it's equal to 333 Kelvin, it's right at the boiling point. Okay? All right, now, what about chemical changes? Well, we've been working only with physical changes, comparing using the number of independent states, which just makes it simple. If we look at the Haber process, okay, entropy will decrease. You have a negative delta S, and that's simply from the fact that we're going from 4 moles of gas to 2 moles of gas. Okay, so just like positional changes that we've seen before, we compare using number of molecules in higher entropy states, which, as we've seen, really is the gases that trump. But if you're looking at solids versus liquids and that's all you have, then liquids are going to trump it. Okay, so again, you're going to have gases that have significantly more than liquids, and then solids are on the way low end. So for example, for this reaction, okay, the entropy would also increase because you're going from 9 moles of gas to 10 moles of gas. Okay, again, it's just counting and looking at those states. All right, if we had to predict the signs of delta S for the following reactions, here we've got calcium carbonate solid decomposing into calcium carbonate solid and carbon dioxide gas. So if we look at those, its S is going to be positive. I don't think you have these answers written down, so you may need to jot these down on your notes. Then if we look at the next one, here we're going from 3 total moles of gas to 2 total moles of gas, so you have a decreasing S and a negative delta S value, which is not so automatic. Okay, assigning S values, normally we deal with changes in S, but we can assign actual S values to substances. This is the third law of thermodynamics, that S is equal to 0 for a perfect crystal at 0 degrees Celsius, which is, absolute 0, which is not really something that we reach, but we can look at it in theory. It's really just a standard value to help us set up S values. Okay, so we start with the basics and then we go from there. Appendix 4, you'll see in the back of the book, contains those S values. You should find those for common substances at 298 Kelvin and 1 atm, which is pretty standard conditions. Since S is a state function, we can simply subtract it and find from final minus initial and get the answer. So here we have another one of our sum problems that we did before. Since we've already done these, you can find one on page 800 that you can look up. It solves plug and chug just like we did with back in delta H and some of those reactions. So, okay, you can find those. Here's 53, 205. You plug it in for delta S and you're good to go. And you get negative 149 joules over Kelvin. Remember, when we do these, this is products minus reactants. That's probably the biggest thing, and these would be numbers that would be given to you, but remember, for right now, you can find them in the back of the book. Okay, last concept, free energy in chemical reactions. Delta G prime change when reactants and products are both in their standard states. We cannot measure it directly, but we can calculate it from other measured values. Refresher on standard states, look on page 260. There's a chart that explains that. But the more negative the delta G prime is, the further the reaction's equilibrium position lies to the right, or that it's going to favor the products, which makes sense because the more negative, the more available energy that got used up, the more it's going to favor the products, and it's going to shift that to that side. Okay, now you got 3 ways to calculate delta G. You can use our equation that we've been doing, plug and chugs. You can find delta H primes and delta S primes in the appendix in the back of the book. Still products minus reactants. You can also put those in the equation. You can also use Hess's law. Okay, you can use delta G values for those equations. They'd obviously happen to be given to you. You also can use the delta G prime standard energy of formation, and that's, again, our sum laws. And then there are some sample problems for you to refer to, and we will do several of these in class that will help us get them more familiar and answer our questions.